Hi, I'm Nathan. I'm a student from UW-Madison. I work in the Silly Linguist Lab. Um, and unfortunately, I wasn't able to make it to the conference in person this year, but I'm very happy to be presenting my work virtually regardless. So I'm going to be talking about phylogenetics today, and I'm going to be talking about sorting trees by their path within a species network and how I'm achieving that in Julia. So first of all, there's a lot of introduction for phylogenetics. But I'm going to briefly sort of skim over all of it. So right here we have a network, and we can see that there are four sort of general types of nodes in this network. There are the leaf nodes, which everyone is hopefully familiar with, and then two special nodes, a root node and a hybrid node. Here, a root node is where essentially where evolution began on this tree. So all of the leaves in this tree are different species, and we can imagine time flowing out from that yellow root node down towards the other ends of the network. Then we also have in this network one hybrid node, and that is the only node in the network that has two branches actually flowing into it. So even though the network is depicted as semi-directed, all all time flows sort of away from that root node and toward each of the leaves. And so that hybrid node is the only node in this network that has two inputs and one output rather than one input, two outputs. So, um, additionally, this hybrid node, I call it a hybrid node, and a hybridization is a specific type of horizontal event or non-tree-like evolutionary event. Um, but even though I call it a hybrid node, it actually refers to any horizontal event. So I'm going to be using that as a blanket term throughout the presentation. Additionally, just to give some more background on what horizontal events are, there are a bunch of different non-vertical or horizontal evolutionary events that can happen between species, including gene flow, introgression, migration, horizontal gene transfer, and hybridization. This is not an exhaustive list, but again, anytime we refer to a hybrid node, that's referring to something that is sort of representing one of these horizontal events. So additionally, we can see that this network has one hybrid node, and there's sort of a circle that forms around that hybrid node that you don't have anywhere else in the network. And we can count the number of nodes in this cycle, and we call that the hybrid cycle length. For any graph theorists, technically this isn't actually a cycle, it's a blob, because even though it's depicted, directions aren't depicted on these branches. This is a semi-directional network, so it's not actually a cycle, it's a blob, but we call it a cycle just because it's more convenient to say. And then here's an example of a network with a cycle length of 4. Then additionally, if we add up the branch lengths of all of the branches that form these cycles, we get what's called a cycle branch length sum. So here we would just add up the branch lengths for all of these branches that are highlighted in each of these networks. Now that we have a little terminology out of the way, we can talk about what our goal is. And so here is another way of representing a species network. This time, we put the beginning of time at the top, or the past at the top and present day at the bottom. And so T1, T2, T3, and T4 here are just placeholder names for existing species. And this network sort of represents their interactions as we go back in time. Now, these branches are sort of popped out like this because we can imagine, rather than one individual evolving throughout this network, we can imagine that each of these branches contains entire populations of species at a time. And within these sort of popped out branches, we can also more conveniently draw genes evolving throughout time. So here, within the network, I've drawn one gene tree that does not follow the horizontal event. And so we can see that there are blue lines and red lines. Each different color represents a different version of that gene. So as the gene evolves and as the species evolve, the gene changes. And so here we see that T3 and T4 have the same version, so they're going to be pretty easily identified through this gene as being closely related, and the same goes for T1 and T2. And so if we were to sample this gene from these species, we might get the gene tree that we see on the right here. Additionally, we can get genes that do follow the horizontal event at some point. And so here we see that maybe, for example, this could be a migration event where some species that were in, that eventually turned into T2 actually migrated over to where some of the ancestors of T3 were at the time and exchanged genes. And in the case of this gene, that changed the course of what the gene looked like for T3. And so now we get a completely different gene tree if we were to sample this gene for these species. So then finally, if we make this a little more complicated by having the gene evolve a couple more times, and we have entire populations of these species existing at once, so we can also have different versions of the gene existing at a single time within a population, we can get some very complicated results like this, where this sort of estimated gene tree, a gene tree that we might estimate shown on the right, is very dissimilar from the relationships that we see in the species network on the left. So when this happens, when we take into account this phenomenon, which is called incomplete lineage sorting, it can be very hard to tell whether or not a given gene has any signal from one of these horizontal events. So it would be very nice if we could take a look at some set of gene trees that we've observed, estimated and observed, that have come from some underlying species network. And it would be great if we were able to mark them as to whether or not they have signal from this horizontal event. So here, yes, there's just the gene trees that do have some signal from this, and no is the ones that don't. This would be very nice for evolutionary biologists because we would be able to more accurately and sort of in a more detailed manner trace the histories of different genes back in time. So I'm going to talk about sort of a progression of algorithms, and we're going to talk about how they build on each other. So a first naive approach to this problem would be to use what are called the species network's displayed trees. So the displayed trees come from either flicking the horizontal events on or off. So here are each of the network's displayed trees. You can see on the left, the horizontal event is not followed at all. And on the right, the horizontal event is followed, and it dominates the other sort of ancestor feeding in that direction. So in the case on the left, we would get a gene tree, or we'd get a species tree that directly reflects the topology of the species network, whereas the species tree on the right might be a little more counter to what we would expect. And so we can think that we have all these estimated gene trees, and we have these two display trees. We would expect each of our estimated gene trees, if they do not have some horizontal event signal, we would expect them to be more similar to the tree on the left. And if they do have some horizontal event signal, we would expect them to be more similar to the tree on the right here. And we have plenty of different distance metrics in phylogenetics. And so a first naive approach could be looking at these displayed trees and just placing a gene tree, saying that it comes from whichever one of these it's closer to. So if it's closer to the species tree on the right here, we would say that it has signal from the horizontal event. And if it's closer to the one on the left, we would say that it does not have signal from the horizontal event. And we can try this, and we get very mixed, not so good results. So I'll talk about the simulation parameters a little bit later, but here are the results for 200 simulated networks using the algorithm I just described and using the Robinson-Folds distance metric. You see that we get very mixed results, and the reason for this is that we actually don't always expect gene trees to be sort of closer to their correct displayed species tree. And that, again, is because what we mentioned earlier with incomplete lineage sorting, it can make the sort of gene trees that we get, that we see, that we estimate, it can make those very complicated because they follow very complicated evolutionary paths. And that leads to mixed results for this method. And 50% accuracy here because we have two groups that we can choose from, and in our simulations, we gave about 50%. 50% of the gene trees came or had horizontal signal, and 50% did not. Here, 50% is the worst we can do. So, your second idea might be, okay, using just displayed trees isn't quite enough, but maybe if we can't expect the tree, if we can't always expect the trees with horizontal signal to be closer to the displayed tree, this displayed species tree with horizontal signal, maybe we can expect them to be closer to the other gene trees that do have horizontal signal. So you would you could calculate something like this, which is a pairwise distance matrix, where each of the rows and columns correspond to one of our estimated gene trees. You could estimate this, or you could calculate this, and then, I don't know about you, but the first thing that jumps into my mind when I have a pairwise distance matrix is clustering. So you could throw this into some generic clustering algorithm like k-means, in this case because we know we're going to have one reticulation here, one hybridization event. So we are going to want two clusters. And so we can throw this into k-means, and if we do that again with our same simulations using Robinson folds, we see that our results actually get worse. So on the left here, this stack of points is using this naive k-means algorithm, whereas the stack of points on the right is using the previously described displayed trees algorithm. So the sort of dark and bold lines, the black lines connect different runs to one another. So the same 200 networks were used with each algorithm, and the lines connect runs of the respective algorithms that were run with the same network. So if displayed trees method did better than the naive k-means, the line goes upwards for that network, and vice versa, the line goes down. And all of the networks where naive k-means did better on this slide, the lines are dark and bolder, whereas where displayed trees did better, they're faded into the background a bit. So we see that in the vast majority of cases, the displayed trees method actually does much better. So it might seem like there's not much hope here for our pairwise distance k-means approach, but that's not actually the case. So if we look here at the displayed trees outcomes, we see that it's pretty uniform between 50 and 100. It's very well spread between within that range. Whereas for the naive k-means outcomes, there's this big gap in the middle where there's only something like 10 points between 65 and 85, whereas there's something closer to 50 for the displayed trees, right? So the reason for this gap is actually because points are being heavily concentrated towards 50% for naive k-means because each network only had one run of the algorithm, and it turns out that naive k-means, when run like this, is very sensitive to the algorithm's initialization, to where the centroids are initialized. And so if we want to be able to use a sort of clustering approach with these pairwise distances, we need to be able to have an approach that does better than this, that is more consistent and stable over time, and in individual runs. So that leads us to our algorithm. And so for our algorithm, we have these estimated gene trees that we've sort of observed from some set of species. And these trees are depicted with orange borders and blue borders. For convenience, the orange border is the trees with horizontal signal, and the blue border is the trees without horizontal signal. And in addition, as we run through many iterations in this algorithm, we're going to be keeping track of a 9 by 9 similarity matrix. 9 by 9 here because we have 9 gene trees. So similar to a pairwise distance matrix, each of the entries correspond to sort of the similarity of pairs of gene trees. So for the algorithm, we're going to have many iterations, and they're all going to look the same. We're going to start by taking a random subset of our estimated gene trees. In this case, we have a random subset of size 6, and we've chosen these gene trees. And we're going to initialize 2 clusters by randomly picking 2 of the gene trees from our subset, from the queue here. And then for each of the remaining gene trees, we are going to compare it to every gene tree that is already placed in a cluster. And we're going to look at what is the average distance from this gene tree being placed to each of the gene trees that's already in the cluster. And we're going to put this gene tree where the average distance is smallest. So in this case, it has an average distance of 2 to cluster 1 and an average distance of 1 to cluster 2. So it goes into cluster 2 because it's closer on average to cluster 2. And here the distance here is just sort of a placeholder, just made up numbers, but you can sub in any distance metric you want here for this algorithm. And so we run through doing this for every single gene tree that's in the queue, placing them. This one's closer to cluster 1, this one's closer to cluster 2, and this one's closer to cluster 1. And we come up with a result. And so once we have a result, we look at each of the gene trees, and we look at the pairs of trees that ended up in the same cluster together. Now, for each pair in this cluster, we increment that pair's index in the similarity matrix by 1. So here we increment all the indices corresponding to the pairs of 1, 4, and 9. And then we do the same for the other cluster. So the idea here is very similar to bootstrapping. We are just doing sort of a bunch of smaller runs, and we're recording the outcomes of those runs, and we're hoping that this will smooth out any of the sort of incorrect runs and incorrect placements of trees. And so we do this many, many times, updating the similarity matrix as we go, and we end up with one final big similarity matrix. So in this case, this would be something of an ideal outcome where we see the first 4 rows and columns correspond to gene trees that have horizontal signal, and the last 5 correspond to gene trees that do not. And so the top left 4x4 quadrant is all high numbers, and the bottom right 5x5 quadrant is all high numbers, whereas the other 2 quadrants are all very low numbers in comparison. So because they're so different, if we throw this matrix into something like k-means, again, we will get a result like this, something very nice, where it places all the gene trees that have horizontal signal with one another and all the gene trees that do not have horizontal signal also with one another. And so now the hope of this is that by sort of essentially bootstrapping this clustering process, we're hoping that we can smooth out these sort of failed runs that we got from the naive k-means approach. And what we see is that this is indeed what happens. Our worst case accuracy jumps extremely high, much higher than both of the other 2 algorithms. And just overall, the distribution is looking much, much better. So now to talk a little bit about the simulation parameters. Like I said, there are 200 networks that we simulated. Each of these has one reticulation, one hybrid node, and they were all simulated with Sci-Fi Network, which is a package in R. They all have inheritance proportions ranging from 0.4 to 0.6. So we expect somewhere from 40% to 60% of all of the simulated gene trees to have horizontal event. And additionally, there are around 2,000 total gene trees for each network. And these were simulated with Phylogenetics simulations in Julia. Now, we should talk a little bit about the distance metric we use here. So Robinson folds is a very commonly used metric in phylogenetics. It's sort of one of the original metrics that people used way back when, and it's still very popular. Everybody knows about it, and just about everybody has used it at some point. But it's over 40 years old, and there has been a lot of good research that has gone into developing different distance metrics in that time. And so we should investigate those and see if we can do any better using those. So we're going to look at two other metrics and see how they do. And the first metric that we're going to look at was proposed by Kendall and Colleen in 2016. And the way that it works is for each pair of leaves in a gene tree, it calculates the distance to the most recent common ancestor that those two leaves share. Then, for any two given trees, the way it calculates the distance between the trees is it looks at each of the all of the pairings for each of the trees, and gets the Euclidean distance between each of the vectors of pairs. And so why are we using this metric? Well, for one thing, it offers more precision than the Robinson-Folds distance. It offers more precision because Robinson-Folds distance is a positive integer. It will always be a positive integer, whereas Kendall-Colleen is a positive decimal. And additionally, Robinson-Folds tends, it heavily depends on the trees you're comparing, of course, but Robinson-Folds tends to be sort of below 15 for the networks that we're comparing. So only integers from 0 to 15 doesn't give us very much sort of coverage or brevity. And so having something that can be a decimal, like this metric, is sort of preferable. And this metric also maintains a direct biological interpretation, which is preferable because we just want to get at least one of these additional metrics that maintains sort of biological interpretation. Then the other metric that we're going to use was proposed by Martin Smith in 2020, and this metric is based in information theory, and it compares trees by looking at how many bipartite splits they have in common, and just using other information theory results to do with phylogenetic splits to calculate their distance from one another. If you're interested, I highly recommend reading the paper. And so why are we using this? It also offers improved precision over Robinson-Folds distance. This is any number ranging from 0 to 1, any real number from 0 to 1. And it was shown in Smith 2020 to outperform many other metrics, and specifically many other commonly used metrics like Robinson-Folds distance in various ways. There will never be probably a metric that does best in every possible way, but the metric proposed by Smith in 2020 does very, very well across the board. So we can plug these distance metrics in, and these are the results that we get, which is more or less what we would expect, right? So Robinson-Folds is an older distance, so it's at the bottom where we expect it to be. Kendall-Colleen, their distance is newer and hopefully better, but it's sort of restricted by its maintaining a biological interpretation. So it might not be as mathematically sort of applicable as something like Smith 2020, which is at the top here. So even though the Smith 2020 metric does not maintain a biological interpretation, it does have the strongest results in our algorithm out of any of the metrics. But we can dive into these results a little deeper. And just to remind you what a cycle length is, a cycle length is this sort of circle that's formed with the hybrid. It's the number of nodes that form the circle. And if we break these results down by cycle length, we see a very stark trend. So this is only showing results from using the Smith 2020 metric. And we can very clearly see that as the cycle length increase, the accuracy tends to increase as well. And so why does this happen? Well, in general, as cycle length increases, what's happening is that the hybridization or the horizontal event in the network is connecting two sides of the network that would otherwise be very, very far apart from one another. So you can see from this huge ring underneath the 12 axis, the 12 on the x-axis, we can see that the sort of from the beginning, basically no matter where the root is coming from there, the hybrid goes a long way in that circle. That circle is very big. And so the horizontal event stretches a very far distance. And so because the horizontal event stretches a very far distance, that the effect of that horizontal event is going to be much greater. And if the effect is greater, we should hopefully be able to more easily discern whether a gene tree was affected or not. And in fact, that is what we see with our algorithm here. But we can break this down a little further because this phenomenon tends to happen as cycle length increases, but specifically when the cycle length is small, we can still have a small cycle length with a horizontal event that stretches a sort of large span. So we can break this down even further by instead looking at the cycle branch length sum. And when we do this, we also get the same trend, but this one is, I think, a bit easier to follow, other than that one little outlier in the bottom right there, which is ruining the whole plot, but it's okay. And then we can also look at this plot for the other distance metrics, and we get more or less the same thing, not as stark of a trend, just because these other two metrics don't perform as well, and it is in general below a cycle branch like sum of 2, where these two metrics get worse performance than the Smith 2020 metric, and so the trend doesn't pop out as much. So that's what I've been working on, and we're very happy with what we have so far, but in the future, we would really like to improve the performance of the algorithm when cycle branch like sums are small, or identify if that's possible at least. We'd also like to evaluate performance on a wider variety of simulated networks. The networks here were all simulated sort of the same way, even though their topologies tended to be very different. There are sort of still a wider variety of networks that we can look at. And additionally, all of these networks only had a single reticulation. And so we'd also like to extend this method to more than one reticulation to see if we can still hold similar results. And so for some acknowledgements for what went into this, for the simulations, Sci-Fi Network was used for network simulations. That's a package in R. Phylogenetics simulations was used for gene tree simulation, which is a package in Julia. And we use these three distance metrics. And for general phylogenetic tools like reading and writing networks, we use Phylogenetics, which is a wonderful package in Julia. And just at the very end here, I just want to shout out my lab, thank everyone in my lab, because they are all phenomenal people studying phylogenetics, microbiomes, other multi-omics topics. And they're all very, very smart and very, very wonderful people. And specifically my advisor, Claudius C. Lemos. And thank you everyone for listening to my talk.